Dear Professor Hamilton, Professor Rafi Bria, my dearest friend, Dr. Yuval Binua, colleagues and friends, I apologize for not being with you to discuss the latest development in the field of medical device innovation. Because of the COVID-19, it is still extremely difficult for me to travel internationally. I would like to present to you the innovation and the development of China's medical devices and the actual status. I would like to present the following 3 items regarding the current status, the trend, and exploration. First of all, the device marketing growth keep with the time. The market size in China's medical device industry was 964 billion in 2021, with a compound growth rate of 27.6%. The global high-end medical device market, for example, in Europe, US, Japan, etc., is the compound growth rate roughly less than 5%, it's roughly only 4%. You will see that, and this still increase very fast in the China market. Secondly, the need is there. That means a high growth rate of the output value. In the recent 5 years, the output value of medical device industry shows a steady growth with a growth rate of about 10 to 15%. The number of medical devices filing and registrations also shows a steady growth trend with a rapid increase in the filing registration number. This trend shows in last from 2013 to 2021. And you will find also the devices mainly accumulated in the area which I will show in the delta, we call the Yangtze Delta area and the Pearl River Delta area. The rapid growing subdivision field, some have taken the leading in this world. For example, the medical devices structure, the medical imaging, IVD, especially low-value devices, and cardiovascular orthopedics. And we found that the medical imaging took about 60%, IVD 14%, and the cardiovascular devices in last years was 6%. The increase in total foreign trade growth also now increases. You will find that from 2015 to 2021, this is shows the blue shows the import, and red shows the export. Both increases, but you will find that the export devices also increases dramatically. In last years, especially in recent 10 years, I believe, the regional agglomeration faced in 3 areas, or we call 3 clusters. One is in the Pearl River Delta. This area is near Hong Kong, Shenzhen, and Guangdong provinces. The second cluster is near Shanghai, with the Yangtze River Delta, we call, in this triangle. And Shanghai as a pioneer, Jiangsu and the Zhejiang provinces also as 2 wings of the development pattern. And the third cluster is Bohai Gulf area, which is Beijing, Tianjin, and in this area. And overall increasing trend we'll find in last, especially 10 years, especially since 2015, because at that time we got a tension relationship with the United States, especially, and therefore the government issues several policies to encourage innovation. And also, China enters aging area or period with the average life expectancy of about 80 years old, and also upgraded medical devices model to promote the development of these medical devices. Yeah, this right side illustrates that the devices in last years from the development trend of AI medical marketing in China from 2018 to 2027. This is the trend estimated in the next years. And the clinic-oriented medical innovation system is built in last years. First of all, is the unmet need or the clinical demand. The second is the value of doctors, especially the clinical physicians, plays in the role in the field of innovation. Third is the role of medical institutions, especially hospitals, universities, plays also important role in the medical innovation in the last 10 years. And as I mentioned, the doctors plays an important role because from the original idea to the R&D to the clinical trials and to the use of these devices, doctors plays an important role. And also the medical institutions and also encourage their colleagues to join the innovation whole system. The integrated development of medical devices will build a medicine, industry, university research in China very mature road. First of all, from the strategic clinical expert to top universities, top enterprises, which joined this clinical-oriented clinical need system. And you will also find under this policy encouragement, in these years, the research hot point also related to the biomedical materials. You see, from before 1980s, we only focus on biological materials. But this year, you will find especially from these years, by the research hot point focus on biocompatibility, mechanical property, medical devices, tissue engineering, and nanophase material, polylactic acid, chitosan, surface modification, and blood compatibility. And this was before was only in this field in biological materials before 1980s. Now I think every field now they put a lot of effort for the research, and according to our statistics, we do find that biomaterials now focus in this six field from chemistry, from basic medicine, from textile and science, chemical engineering, and so on and so on. Four, the integration of AIs and medical devices now also entering the clinical practice. We have in China several industries. They're focusing the artificial intelligence in the use of medical evaluation and to judge for the therapeutics and to help us for the post-operative rehabilitation. And the next one is that we are now focused on the global layout, insist on global innovation. The Chinese medical companies gradually focus on now the international marketing layout, and the innovative products are constantly emerging. The number of transactions in the category of medical and life sciences also increases dramatically in the recent several years. We have built the systems with international companies such as Medtronic, Siemens, and so on. Yeah, the third point I want to point it out regarding the exploration of cardiovascular medical devices innovation in China. You will find that since 2009, the mortality of cardiovascular disease increases dramatically, but we found a phenomenon that in the rural areas, it overcomes of the urban areas. This is because more and more people, they have dyslipidemia, diabetes, and smoking not really well controlled, and hypertension is not very well get controlled. Therefore, in the rural areas, the health system is compared to the large cities, to the urban areas, they are still underdeveloped. Therefore, it's leading to the mortality in the rural areas increases dramatically. This is the need. Therefore, we now in the next years should focus especially on the middle and west part of China, and because the mortality which contributed to all mortality in China, cardiovascular disease, no matter in the urban area and the rural areas, overcome. It takes about more than 40%. And we do also find we have our own the disease spectrum. For example, this is the statistics of aortic valve stenosis. You will find that bicuspid valve in the US only takes about 1.8%, or in Europe, 4 to 5% of all the aortic stenosis. But we do find now in all our aortic stenosis, bicuspid valve takes about 37%. This might probably a paradox of because the patient is younger, first, secondly, and we are now just enter the aging period in the recent years. This may be changed the proportion in the future, but now this is the actual situation. Therefore, in 2015, I called colleagues from China. We have founded a club for cardiovascular innovation. We call Center for Cardiovascular Innovation. In this foundation was in September 11th, 2015. We, based on the previous experience, we do find that all the innovations should come from the first-line doctors. In the last 7 years, we have built a mature system, and in the early days, we raised our slogans from the doctors, by the doctors, for the doctors. This is the CCI. It's a mission. And now, since last year, we built our innovation center, and we raised that our concept is from the doctors, by the engineers. The purpose is for the patient. And you see, from 2015, we found this CCI, and in next year, we build the Academy of Innovation. And each year, we hold our competition, and we build close international relationships with our international colleagues. I have to really appreciate Professor Jaime Lotan, Professor Raphael Beer, and Dr. Binua for the support in last years to build our system. And by 2020, we build our EMEDIC, the Eastern Medical Device Innovation Center, which try to help all our fellows to structure their innovation. And last year, our CCI, we acquired a place, and we built our experimental center for the animal device testing. And by the end of last year, we compiled a white paper on China's medical innovation. And this could be really book conduct the medical innovation in China. And you will find in the last 7 years, we had trained about 470 trainees each year, and they are clinical first-line physicians, engineers, and enterprises. And you will find that by this year, we have 84 fellows now under training, and we now build a system to train our fellows how to protect their own property and how to transact their product from a prototype to a really clinical device. And this is all the pictures we had. This you see, find this is Dr. Benoit, this is Peggy Wang, and we all the fellows, they are graduated. They have to send their patent to for our review. And then after we build the incubation platform, that's the Center of Excellence for in cardiovascular innovation. And we build, as I mentioned, a mature system for project mining, project evaluation, patent application, prototype manufacture, and transfer this for the industrial support. And for example, this innovation is not always easy. From the first biodegradable stand in China, and in 2005, we start our experimental study and patent. And after about 7 years experimental study, and we are allowed to do first in human. And our Premier Li, he asked twice for this device. And by March 2020, after 15 years after, it got launched and approved by the local MPA. This is a local FDA. And our fellows created the first cryoablation catheter for the renal denervation to treat persistent hypertension. And our fellows, they developed a novel ultra small catheter FFR system, which is mounted on a monorail catheter, which is more user friendly and user friendly. And our fellow also developed we call valve clamp, and which is apical device, which to catch the mitral valve easier than that of device existed now. And we finished all the clinical investigation and are waiting for the governmental approval. And we also, the fellow, developed a very nice device which treat the tricuspid regurgitation, because you know, the tricuspid valve or the annulus, it is very difficult to fix, and not a single device which could better than the other. But this device, we have a flap which we mounted on the septum to fix this the valve, and we have two. We call the ear, which fix on the valve, and this is very soft. During the remodeling of the right atrium and right ventricle, which it is could follows the tricuspid annulus to reform, to decrease the size. And I do believe this is one of the best devices which treat the tricuspid valve. We do this transjugular through the TE monitoring. And yeah, to summarize, that the innovation chain in China of CCI, we first to build, ask our fellows to build the concept, and then for the device validation, and afterwards we transfer to the industry. Therefore, the MDIC, the Eastern Medical Device Innovation Center, which was built 2 years ago, just to finish from the phase from 10 to 100, and the CCI finished the phase 1 to 10, and the original we come from our fellows from 0 to 1 that we call the original innovation. And the system of CCI in last 7 years, we build our core is the combination of medicine and engineering. And this could be composed of 2 systems. One is the theoretical system, one is the practice system, and which we do believe will promote the domestic medical innovation ecosystem in the following years. So as I mentioned, from last year, I raised our slogans. The concept is from the doctors, and the prototype is by the engineers and the industry, and the purpose of every device or innovation is for the patient quality of life. Thank you very much.
Hello, everyone. It's my honor and pleasure to be here today with you in this special ICI CCI session during CIT 2021. We started our cooperation, as you can see already 7-8 years ago, with the unique sessions at ICI. And in the last 2 years, despite the corona that affected the entire world, we still continue with our innovation. As we can see, the biotechnology revolution is continue, and the biotech market is growing very quickly. Heart disease is growing especially, and it's the #1 killer both in the United States and even in China. And I just learned that every day, almost 7,000 Chinese people are dying from heart disease. And there is a big pandemic of overweight and diabetes. The needs are very big in cardiology, valvular heart disease, sudden cardiac death, hypertension, heart failure, telemedicine, and diabetes. As we can see, the population is aging and people want to live better and longer. In the ICI, it's innovation for cardiovascular intervention. We show the latest breakthrough from an idea all the way to reality. Why in Israel? Because Israel is a startup nation, and a lot of the innovation in cardiology are coming from Israel. And I'll show you some of the latest things in the last ICI regarding innovations in cardiology. We'll talk a little bit about cath lab of the future, robotics, imaging, AI, structural heart disease, which is expanding, devices for peripheral vascular, neuro, heart failure, and digital. We can see that the cath lab is becoming more and more robotic with corridors, with non-invasive assessment from coronary CT scan. As you can see, you can predict the entire flow in the artery. And another company, CathWorks, is taking the angiogram and showing you from the angiogram the nice evolution of FFR in all the arteries. We also have improvement in augmented reality, trying to see with virtual assistants what's going in the chest. And ultrasound, ultrasight, is a very unique company that can take you and do cardiac ultrasound anywhere by analysis using AI, the entire system, and even someone that doesn't know how to do echo can be directed to do the echo with very good results. Another problem is electrophysiology. As you can see, the electrophysiologist has to take care about a lot of things, the ablation, the mapping, the pacing, and a lot of monitors in the cath lab. And today, this company is coming with virtual reality, putting all of them in the glasses of the operator, enabling him to do the procedure in a much better way. Structural heart disease, as one can imagine, is really booming. We have finished almost the area of aortic valve, and now we are going into the mitral valve and tricuspid valve with a lot of new companies. For example, Valtech Cardioband has developed a very nice C-shaped kind of band for fixation of the mitral annulus. We have Valker, which again developed a transcatheter way to implant a D-shaped ring into the mitral annulus and constrict the annulus and improve mitral incompetence. And a new company, Innovalve, today is replacing the older valve. Valfix Medical is gripping again the entire annulus, constricting it to improve in patients with mitral incompetence. Tricuspid incompetence is also very important, and there is a new tricuspid valve repair system, which is called TriPair. And as you can see here, you have a system which is implanted in the middle of the tricuspid valve, and with this, you can eliminate or reduce the amount of tricuspid incompetence. It's effective, very quick, atraumatic, and even can be retrieved. There is another company that is looking for aortic incompetence, a problem that is quite significant in China, trying to find a solution for aortic regurgitation. As we can see here, no calcification, but a lot of regurgitation. And their idea is to add another cusp to one of the existing cusps, and this cusp will prevent artificial cusp, which is attached, will prevent the aortic incompetence. Nightingale Medical is another nitinol-thin new tricuspid valve, and as you can see here, it can land on the tricuspid valve, be attached to it, and prevent. Another Israeli company is called Trizol, which has done already first in man, and you can see this coming through the tricuspid valve, attaching backwards, and slowly implanting a new tricuspid valve with very good results. There are several new devices for peripheral vascular disease and neuro. As you can see, Invatin is a company that has developed removable and replaceable filters. This is going to be a major issue in aortic valve replacement. And we have like this several companies already in different stages. The Emboliner catheter and the Filtrex catheter, all of them have run already through first in man, and now they are in pivotal studies. There are new devices also for peripheral vascular disease and neuro. As you can see here, this is Nexus, which is the first endovascular repair of the aortic arch. You can do everything in type A aortic dissection, enabling flow into the aortic arch, the main branches, and they have finalized 30 patients going for a CE. Another problem is erectile dysfunction, and Sanofi has developed a way to deal with venous leak. It's an in-office, very simple way to constrict the dorsal vein of the penis and elevate the pressure in patients who has venous leak. Heart failure is a very big issue. A lot of devices also to monitor and treat heart failure. Donisic company is a monitoring company, which is a safety net to keep those patients at home. They measure a lot of parameters, skin, temperature, saturation, heart rate, etc., and can really alarm when the patient is deteriorating. The VLAP system by Victorious is another system, which is a microcomputer which is implanted in the left atrium, as you can see, very smallly, less than a penny. It provides you away, as you can see here, very, very small, and it gives you a continuous reading of the left atrial pressure. And if the patient deteriorates, the physician can get alarmed that the pressure in the left atrium is deteriorating. And as you can see, the data from this small computer is sent to the patient application to the physician and can be treated online. And this is the way to do personalized medicine. Another system which has been developed together with our friends and colleagues at Innova is the Noya system, which is a shunt, a way to do a shunt between the left atrium and the right atrium using RF to reduce pressure in the left atrial site. Another very important part is the digital health revolution. Alio is a company which has a wearable platform to improve the outcome and clinical flow. It's smart patches that can give you all the information that you need about heart rate variability, saturation, blood pressure, etc. Everything goes through the computer to the cloud worldwide, and the physician can get all the information and treat it. And as we know, digital health will revolutionize the way we are doing medicine with a lot of devices. This is used already for treating patients with diabetes, heart failure, and obstructive pulmonary heart disease. And there are a lot of devices that were shown, like a ring that can do an entire ECG, or cardiac sense, which can measure heart rate, saturation, arrhythmia, PPG, total ECG, etc., and send everything to the cloud. So there were several companies showing that telemedicine is going to change the world, where you take all the data from the monitor through the internet to the cloud, and then also incorporate the glucose, the scale, the blood pressure, and then send it to the doctor in order to improve way. Cardiac care is another digital wear which actually gives you autonomic modulation of the vagus. We know that the vagus is very important in atrial fibrillation. And here, when you have an episode of atrial fibrillation, you can get back stimulation to the vagus and shown to decrease atrial fibrillation episode. So this is just a very small glimpse of all the technologies that were shown in the ICI. Invite to attend our upcoming meeting, which will be in December 4 to 6 in Tel Aviv. Hopefully the corona will be over, and we'll be happy to see all of you and view all the new innovation in Tel Aviv. Thank you very much.
Hello, everyone. Thanks for ICI invitation. My presentation title is New Endovascular Stent Graft Treatment for Stanford Type A Aortic Dissection. The content includes 3 parts: background, animal trial, film study. Stanford Type A aortic dissection is a very dangerous disease, and the traditional treatment method is open surgery. In recent years, with the development of endovascular technology, some scholars began to explore the use of endovascular approach to treatment Stanford Type A dissection. At the same time, for the problem of dissection in the distal aorta, petticoat technology has also achieved good clinical results. Stanford Type A aortic dissection intravascular remodeling system, Shenzhen Changxin Medical Technology Company Limited, Shenzhen, China, includes 2 kinds of stent systems. One is A-type stent system, as shown in Figure 1, used to seal the entry tear location of ascending aorta and open the true lumen. And the other is C-type stent system, as shown in Fig 2, used to seal the distal entry tear location and open the true lumen. A-type stent adopts three-segment structure design. The proximal and distal end are stent graft parts, and the middle part is bare metal stent segment. C-type stent adopts two-segment structure design. One end is bare metal segment, and the other end is stent graft part. Fig 3 shows our solution designed for the type A dissection. With the A-type and the C-type stents combined to solve the proximal and distal end of the aortic dissection. The combination of the two systems provides a new treatment method for the whole aorta. The stent graft part on the stent was used to seal the entry tear, and the bare stent part to ensure blood supply to the branch vessels. The stent is made up of nitinol and PET film with a maximum diameter of 46 mm and a maximum length of 320 mm. Animal trial includes 12 pigs, 3 follow-up 1 month, 3 follow-up 3 months, and 6 follow-up 6 months. Post-operative DSA showed the status of the stent and the branch vessels. 6 months of CTA showed good stent stability, good blood supply to the branch vessels, and no stent displacement. Pathological analysis at 3 and 6 months showed the safety of the stent. Animal trial results showed: first, pigs all in good condition, no death during follow-up. Second, stent design is safe, blood flow in all branches in good condition. 3. Animal trial validate the safety of stent and delivery system. We have done 3 cases in film study. They were all Stanford type A aortic dissection. Case 1. Entry tear near left subclavian artery. Tearing retrograde to ascending aorta. Post-operative DSA showed the stent occlusion. Effect was good, and the true lumen became large. The results of the 35-day follow-up showed good stent status, good blood supply from the branch vessels, and no significant displacement of the stent. Case 2 was similar to Case 1. The entry tear near left subclavian artery, and the ascending aorta was also involved by the dissection. Post-operative DSA showed a little endo leak. We were suggested to wait for follow-up results without further treatment. "35 days follow-up results showed the endo leak became smaller. Case 3 was a PAU. A-type stent was placed 34 days. Follow-up results showed there was no stent displacement. Hematoincus became smaller. 3 cases film study showed. First, the surgical success rate was 100%. 30-day mortality was 0. Second, stent design is safe. Blood flow in all branches in good condition. Third, film study validates the early safety and efficiency of stent and delivery system. Thanks, everyone.
Dear Chairman, dear colleague, it's my privilege to remotely join the ICI meeting. My name is Shenqian Tu from Shanghai Jiaotong University. This is my disclosure. The Phase 3 China shows that QFR guided strategy for lesion selection improved 1-year clinical outcome compared with standard angiographic guidance. Meanwhile, we made a new QFR version which overcome the problem in bifurcation analysis. In the first generation of QFR, since side branches are not reconstructed, a linear tapering reference vessel is used, which might lead to either overestimation or underestimation of lesion severity at the bifurcation. In the new generation of QFR, we call it Mueller law-based QFR or MuQFR. All side branches are reconstructed and the step-down reference diameter function is used in the computation of QFR. This improves the accuracy of QFR computation. In addition, we made work with a single angiographic view. This improves the feasibility of QFR analysis, since sometimes it is not easy to obtain 2 good angiographic views with minimal overlap and foreshortening. Finally, using artificial intelligence, the frame counting were automatic. This improved the efficiency. The average analysis time for MuQFR analysis takes only 1 minute. Using the Phase 2 China study population, we showed that the single-view QFR had a diagnostic accuracy of 93%, which was significantly higher than the QCA derived diameter stenosis. In addition, due to the use of the artificial intelligence to automate the procedure, the MuQFR analysis was reproducible, which we had a low inter- and inter-observability. How about the single-view QFR compared to 3D QFR? So this is a study that was just published by the Journal of SCAR. In this study, we compare the single-view QFR calculated from one of the protocol recommended angiographic projection, and then we using 2 projections to reconstruct the most sophisticated 3D model. So the main vessel and side branch are reconstructed, and then compare the 3 value with FFI as reference standard. In this case, as you can see, numerically, 3 value has some small difference. However, all suggest that the vessel is hemodynamically significant. So this is the main result. As you can see, that single-view QFR calculated from one of the protocol recommended projection had the same or comparable diagnostic performance as 3D MuQFR. This was confirmed by the colleague in Belgium and in Spain in the post-hoc analysis that shows that their diagnostic concordance between 2D and 3D were excellent. However, the 3D analysis, the feasibility in post-hoc analysis was lower due to the lack of second projection. We also applied the algorithm to CT. This is a study that just recently published. We saw that the MuQFR calculated from a single angiographic view has a slightly higher accuracy than the CT-based QFR, CTQFR. The colleague in Zhongshan Hospital also used the MuQFR in the assessment of coronary bifurcation lesion during PCI and showed that it was feasible and safe. So can we do more with artificial intelligence? We had another concept. I can perhaps explain with this example. So when there was a vulnerable plaque there will be higher strength at the superficial wall. This will reflect in the lumen deformation. So the maximum lumen deformation will increase if there's vulnerable plaque. This luminal change is actually hidden in the dynamic coronary angiogram. And if we can extract this small detail, we can quantify the wall strength in radial direction. We call it as radial wall strength, RWS. So the RWS can reflect the vulnerability of the plaque behind the lesion. So we have implemented this concept in the Angioplus core software by Postmedical. So after single view mu-QFR computation, if the image quality is good, by a single click you can get a color-coded radial wall strength distribution map. It is co-registered with coronary angiogram. So the red spot here indicate that at this position, the plaque behind this lesion is risky plaque. So this is now possible with the use of AI. We have completed a few validation studies. In this study, the angiographic-based RWS is compared with OCT-derived RWS using finite element analysis. As you can see from the figure at the lower side, there was a good correlation in RWS derived by angiogram versus by OCT, and it can differentiate the healthy segment and the disease segment. And this is another study that was just published by Eurointervention. We saw that the angiography-based RWS can identify vulnerable plaque defined by OCT, either by the lipid to cap ratio LCR or by TACFAR. I want to give a few words about LCR. It's a new vulnerability index that can be computed automatically from OCT by using artificial intelligence. We propose this new index to address the limitation of TACFAR. And let me explain it with these two examples. By the definition of TACFAR, plaque A is a TACFAR, while plaque B is not a TACFAR. However, clinically, plaque B has higher risk since there's such a large lipid plaque burden behind. So instead, the LCR is computed by dividing the lipid plaque burden by the cap thickness. It's continuous variable, and the higher LCR, the higher risk. In this case, plaque B has a higher risk than plaque A. But how did this parameter perform in practice? In this study that was just published in JACC Asia, we observed that LCR had a higher hazard ratio than TACFAR in predicting 2-year MASH for non-covered vessel in ACS patients. So the hazard ratio for LCR is 19.13, while for TACFAR is only 2.77. This is another study in collaboration with Shibo from Fuwei Hospital. We found that the RWS was an independent predictor for fast lesion progression, which adjusts hazard ratio of 7.112. In analysis of phase 3 China data, we also found that in non-flow limiting vessel with RWS larger than 12% had a higher event rate than those vessels with lower RWS. Ladies and gentlemen, in conclusion, mu-QFR and RWS can rapidly compute from a single angiographic projection for accurate assessment of flow-limiting epicardial vessel and lesion vulnerability. Single-view mu-QFR and two-view 3D mu-QFR had comparable good diagnostic performance in identifying hemodynamically significant coronary stenosis. High RWS identified vulnerable plaque defined by OCT, and was independently associated with intermediate lesion progression, where low RWS in non-flow limiting mild coronary narrowing was
Hello, everyone. My name is Alan Tsai. I'm the General Manager of Cordis China. It's my honor today to give you an update about Cordis. Cordis has over 60 years of legacy committed in pioneering breakthrough interventional cardiovascular technologies. We are the one who invented the first guiding catheter and coronary drug eluting stent. Globally, we have our footprint that spans 70 countries to provide our products and service to healthcare professionals and serve our patients. Cordis has become an independent company since last year, which allows us to focus on the interventional cardiovascular areas to come up with more innovations. In collaboration with Cordis X, an independent innovation accelerator with a go-to-market model built for speed, agility, and value maximization, we are ready to push the envelope and iterate at pace with the market. We will continue to focus on vascular closure, radial and pedal access, and intervention as we look into the future to address the toughest cardiovascular challenges. There are so many number one in our history. In 1966, we introduced the first guiding catheter to the market. In 2002, we introduced the first DES. We are proud that historically, we have several innovative products to shape the industry and drive the development of interventional cardiovascular treatment. Nowadays, we provide a wide range of portfolio that is used in cardiovascular and endovascular procedures. Innovation is the DNA of Cordis. Being an independent company with a clear focus on interventional cardiovascular space, Cordis will bring more innovative products to the market in the future. To drive the innovation and meet clinical needs, we aggressively leverage internal and external resources to bring a stronger portfolio to the market. For example, we partnership with Kanaka to provide a cutting-edge PDCA balloon to cardiologists. We also bring microcatheter to China market through the collaboration with CardioLink Science. Besides, to accelerate the innovation process, we set up a $300 million fund of Cordis X as an incubator in California to search for new interventional technologies, aiming to commercialize them in a quicker manner and bring them to the market as soon as possible. We had some early stories in the last 12 months, a quite remarkable achievement in my opinion, considering new Cordis was only set up in last August. I will introduce the result in the next slide. The first one is our strategic investment in E2, a next generation thrombectomy devices that treat patients with deep vein thrombosis and primary embolism. The second one is our investment in Adient, a fully absorbable IVC filter. We believe in the areas of DVT, PE treatment, and embolic protection. The demand for products with better clinical outcome is strong. Our investment in these areas will help us to serve more patients and satisfy clinical unmet needs. Last month, we announced the acquisition of Medalines, a pioneer in pseudogenous eluting technologies. This technology can be widely applied in different platforms, such as balloon, stent, for treating disease across specialties, such as neuro, cardio, and endo. Its products solution SLR has got a CE approval to be applied in the treatment of peripheral artery disease in February 2020. The second CE mark for the treatment of coronary artery disease was awarded in May 2020. After our acquisition announcement in October, Solution SLR received FDA IDE approval for coronary in-stent restenosis. This allows Medalines to begin the clinical study required for US approval to use Solution SLR in coronary ISR indication. This is the first sustained 3-month release coronary drug eluting balloons to receive FDA IDE approval for coronary ISR. This is the third IDE approval Meta Alliance has received for the solution SLR. We'll also bring a very innovative radio access solution for cardiologists next year to China, the Radio 360. It includes railway, ranges, and infinity. As you know, that more than 90% of the interventional cardio procedure are done in radio access in China. We believe the introduction of this portfolio will bring great benefits to patients and doctors here. Thanks for listening. Hopefully, my sharing about the innovative future of Cordis today has helped you to understand the new Cordis more. Thank you.
Hello, everyone in ICI. This is Yuling from DKMedTech. Today, I'm representing CCI to introduce a new scoring drug-coated balloon for you. The background to introduce this device is because for AV access stenosis, if we use traditional or conventional balloon to dilate the stenosis, the primary patency is low and the clinical burden of the repeated intervention is high. Some other company like Medtronic and Bach, they develop drug-coated balloon to use on AV access, which will prolong the primary patency. But as we know from coronary intervention or peripheral intervention, the best way to use DCB is, before using DCB, you need scoring balloon to prepare the lesion to reduce the stenosis as low as possible. But the main challenge for a scoring balloon in AV fistula is it requires a very high flexibility. Sometimes the balloon needs to turn like 180-degree turn. So DKMedTech, we design a scoring balloon dedicated for AV access. There are 3 scoring elements bonded on the balloon. The elements are made by nitinol coils, which with triangle cross-section. So it can maintain a very high pressure to the vessel wall while maintaining a good flexibility. So from this video, we can see before inflation, the flexibility of a balloon is good. It can turn 180 degrees. But when balloon is inflated, as the scoring elements are bonded on the balloon, it also can conform to the vessel wall to any shape. So on top of the scoring balloon, we coat paclitaxel on the balloon with 3 microgram per square millimeter for the dosage. We design a RCT comparing scoring drug-coated balloon with high-pressure balloon made by Abbott. And this trial includes 10 clinical sites in China. It is 1-to-1 randomized trial with superiority design. The key points of this trial is this is the first DCB in the world. There's no predilation is required. The result of this trial is surprisingly good. The primary endpoint, which is target lesion primary patency at 6 months, we gained the result of a scoring balloon with more than 80% patency, while the control group PTA is less than 60%. And in terms of the secondary endpoint, like device success and acute lumen gain, all these 2 aspects, scoring DCB shows better result. And if we compare the clinical results with the impact results published in New England, we found out the results are very similar and comparable. But don't forget the condition is different because the scoring DCB doesn't require any predilation, while the impact AV design, they includes the patients with 100% predilation success. And especially for the AVG subgroup, the target lesion primary patency shows more advantage. At the 6 months result, you can see the primary patency is close to 80%, while the control group of PDA is less than 30%. And if we continue our follow-up to 12 months, you will see the primary patency of the scoring DCB maintains like 65%, while the primary patency of control group is reduced to 23%. And the conclusion for this presentation is drug-coated balloon has a high potential in AV access, and scoring balloon plus drug-coated balloon is a kind of optimal combination for this treatment. And DK Medtech has developed a high-pressure scoring drug-coated balloon, which is dedicated for AV access. And the pre-market RCT result shows this device can achieve a high lumen gain, high success of device, and a high patency. So sorry that I can't join you on site. I hope to visit ICI next year. Thanks.
Hello, everyone. This is Jianan Li from Chinese Academy of Sciences and Shenzhen Vivalite Meditech. I'm going to introduce our OCT-based intramodal multimodality imaging technology. As we know, OCT as one of fast emerging intracoronary imaging modality has been proven reducing mortality and leading better prognosis. The standardized MLD MAX procedure is established, and it alters 88% decision-making during the whole PCI workflow. On the other hand, with the help of intracoronary imaging, we have better understand of the pathways of coronary artery disease. For example, we know that 30% is due to erosion, and 60% is rupture of the plaques. However, we are still far from a fully understanding of the atherosclerosis plaque, its progression, its natural history, the complete risk factor. Is that possible to detect it at the subclinical stage? Is that to do primary prevention based on risk factor? So the question is why some plaques are vulnerable? Who should be targeted for vulnerable plaque detection, and how should we treat that? There are many attempts by using non-invasive and invasive imaging to try to detect vulnerable plaque at the early stage. For example, the LPR study, the combined study, a lot of them involves the combination of more than one imaging modality. Indeed, the multi-modality imaging could reveal more information from different dimensions, morphology, the physiology, and the plaque composition. So it could be the way out for us to have a better understanding of the vulnerable plaque, to study the vulnerable plaque. There are examples of IVUS nurse imaging. There are examples of OCT IVUS in Lancaster. But the question is, does this mean that the patient and the clinician has to accept more complicated procedure and higher cost? our way is to try to develop so-called intramodal multimodality imaging based on OCT. So with a single OCT equipment and single OCT caster, we could acquire OCT signal and image. And from this, we can derive, for example, the index of plaque attenuation, which is linked to plaque composition vulnerability. We can develop the virtual flow ratio, we call it VFR, the physiology indicator. And also with the help of AI, we can augment our image to get more information. So it is a OCT system, OCT pullback, but we try to dig out more information, multi-dimensional information from the original signal and image. First of all, I'm going to introduce this IPA technology. It was firstly invented by Dr. Gijs van Soest, Erasmus Medical Center in the Netherlands in 2016, I think. Basically, it detects the tissue heterogeneity related optical attenuation from the OCT raw signal. It has been proven to have a better predictive power of the lipid distribution. This is the software interface we developed together with Dr. Gijs van Soest. We implemented it in our newest OCT system. You can see after a pullback, a side-by-side display at left is OCT cross-sectional image, and on the right is corresponding IPA image. You can also check the IPA value of at different position of the pullback. Together with PLA General Hospital, we try to validate this new technology. We did a retrospect study to find out optimal cutoff value for unstable plaque and stable plaque. Then we did a comparison between IPA calculation, OCT structural image, and the corresponding histology based on cadaver imaging. We could acquire nearly 500 frames, and for each frame, we do the histology and to try to link these three modalities to check if IPA result is accurate or not. This is one of the example. Here you can see IPA is not sensitive to calcium, which is correct. However, on the OCT image, it's hard to identify the macrophage clustering, which is shown on this CD68. But IPA, the high IPA region clearly indicate this feature. That's the power of IPA to reveal some subtle feature, sometimes beyond resolution feature that links to the vulnerability of the plaque. This result is going to be published soon. The second modality is the virtual flow ratio. Basically, we try to calculate the flow ratio value from the comprehensive OCT morphology imaging. And this is the interface. After pullback, the VFR value is calculated at every position of the pullback automatically. We validated this, and it's shown a great agreement with FFR measurement. Its accuracy is pretty high. This is one real-world case. So pre-PCI, both QFR and VFR shows a value of 0.78. The OCT MA is 1.37 millimeter square millimeter. So the clinician implement a BRS, and after the BRS implementation, the VFR value rise to 0.95. MA-LA is also drastically expanded. So the third one is the AI and the augmentation. Basically, we know that every image or information has to be interpreted by the clinician during the PCR. So it's very important to automate some of this to try to support their real-time decision making. For example, we know there's an OCT-based calcium scoring system, but in fact, it's nearly impossible to do this in real time because it's quite time consuming. The clinician have to check the image carefully to calculate this calcium score. But with the help of artificial intelligence, we developed this ICI functionality. It can calculate the calcium score within 12 seconds compared to 1 hour manual calculation. So that makes it possible to report this calcium score right after pullback to support the decision making of the clinician. We further push this forward to try to study the calcium volume and the relationship between calcium volume and stent expansion. Based on the image with the deep learning methodology, we can calculate the total calcium volume of the lesion. We study the relationship between the volume and the stent expansion and show that it's a good predictor for the stent expansion. This result is already published. Besides this, we are more functionality related to the AI-based augmentation. For example, the quantification of osteum, automated BRS visualization, automated stent malposition and expansion analysis. We have this pre and post PCI comparison. So you can check the frame one by one to see what happened after intervention. We also have this automated neo-intimal coverage analysis to see if the stent is well covered by the neo-intimal, and this is also automated. In the future, I think we will continue to try to develop our multimodality imaging technology to try to fully understand the structure and the physiology of the atherosclerosis plaque. Maybe we will hit the limit of the intramode method, the limit of OCT itself. So perhaps we have to move to the intermode multimodality, but we would like to stick to the idea by using a single optic fiber to acquire different information. For example, a single optical fiber could collect OCT structural image and near-infrared autofluorescence image. This work has been done by Dr. Jeffrey. We share his perspective that a deeper understanding of plaque pathobiology will lead to a new era of personalized therapy. So basically that's all. Thank you.
In this presentation, I would like to share with you a few observations on the impact of the current global situation on medical innovations. The last 3 years can be characterized as unstable, challenging, and unpredictable. What we are facing is the creation of a new world order, a process that started way before the pandemic. COVID served as a catalyst to this process. We tend to look on the COVID pandemic as responsible for many of our current problems, but I think it is incorrect. It is the attempt to create a new world order that is affecting our lives altogether and indirectly create an impact also on innovations. There are powerful conflicting forces as well as lots of egos driving these global changes. We all have to find ways to continue the innovation stream under these constraints. Medical innovations, like growing mushrooms, require an ecosystem in which it can grow and prosper. Specifically, it requires financial stability and globalization. Economic instability reduces or at time eliminates altogether the funding ability for early-stage innovations. The COVID pandemic had negative impacts on innovations, among them travel restrictions and difficulties in conducting large clinical studies. But it had also a positive side into it, for example, more reliance on digital health, using big data, increased public awareness, and more budgets to hospitals. It is for a long time that the classical venture capital model is not adequate for medical innovation. The pandemic only enhanced the lack of alignment between classical VC and startup. On top of the big issues, startups are facing specific difficulties. For example, the MDRs are in shambles, clinical studies prices have been skyrocketing, supply lines have been broken. China, that has been a major financier of venture capital, a major supplier of components, and a rising clinical center with huge patient population, is basically shut down now, a closure that may be of long duration. The combination of all this created a gap between raising seed money from family and friends or from government-backed incubators, as the case in Israel, and the need for these startups to do Series A or Series B funding to prepare for first in human. Effectively, corporate venture capital entered this funding game, but by the nature of the beast, the span of attention they can give to startups is very limited. While all this may sound very pessimistic, remember that crises do create also opportunities. There's nothing more symbolic, I think, than the Mandarin word for crisis consists of two characters. One of them say hazard, danger, and the second one means opportunity. Altogether, it's defined as weiji, which is crisis. In summary, I think we need to adapt very quickly to the changes in the environment and to keep the pipeline of innovation alive. This is our lifeline. Thank you very much.